vocabulary of structural engineering, bamboo is a biological paradox. It is an evolutionary anomaly that defies the logic of material science. By weight, this colossal grass possesses a tensile strength that rivals mild steel and a compression tolerance that embarrasses industrial concrete. Its outer skin is a jagged armor of biogenic silica, essentially a layer of glass sharp enough to slice flesh and hard enough to dull a commercial chainsaw in mere seconds. It is nature's reinforced concrete, a rigid, hollow iron pipe designed by evolution to survive typhoons, earthquakes, and the crushing weight of snow. Yet, if you are wearing a high-end luxury t-shirt today, there is a statistical probability you are wearing that very same pipe against your skin. The industrial challenge here is staggering. The question isn't just how we transmute a rock-hard grass culm into a fiber softer than Egyptian cotton. The question is how we achieve this alchemy mechanically, without dissolving the plant in a caustic bath of toxic solvents, like carbon sulfide, the legacy method that turned rivers black. We are attempting to break the plant without breaking the planet. Welcome to the bleeding edge of textile engineering. Inside this monolithic, sterile processing facility, we are witnessing the holy grail of sustainable manufacturing, mechanical fractionation. This is not a lumberyard, and it is certainly not a farm. It is a high-velocity physics laboratory where heat, hydraulic pressure, and kinetic energy dismantle nature's toughest architecture, one molecule at a time. Over the next 20 minutes, we will track a single, mud-caked trunk through a relentless gauntlet of laser-guided guillotines, supersonic planers, and pressurized thermal reactors. We will watch as brute force meets surgical precision to unlock the cellulose hidden inside the world's toughest grass. The journey begins at the intake ramp of the processing facility, a chaotic staging ground where the organic world collides with industrial order. Here, raw bamboo trunks, freshly harvested from the surrounding highlands, arrive in a state of wild disarray. They are caked in heavy field mud, curved by years of wind stress, and vary wildly in diameter. To a carpenter, this biological variance is character. To an automated industrial line, it is a nightmare. Machines demand uniformity. Nature offers only chaos. Our first objective is to beat the chaos out of the equation. The first line of defense is the Wusung high-speed auto crosscutter. This unit is essentially a laser-guided guillotine designed to impose rigid geometric order on the organic input. As the raw trunks roll onto the heavy-duty steel conveyor, they aren't just moved, they are interrogated. Above the belt, a bank of sensors utilizing laser interferometry scans the length of each culm at a blistering 200 scans per second. A grid of red laser lines paints the bark, creating a 3D topographic map of the timber in real time. They are hunting for the bamboo's nodes, the internal horizontal knuckles that act as the plant's structural bulkheads. These nodes are denser than granite. If a saw blade strikes a node directly at high speed, the bamboo will shatter like tempered glass, sending dangerous shrapnel into the machinery and ruining the fiber yield. The central computer calculates the safe zones, the internodes, and adjusts the feed position instantly, locking in the cut coordinates with sub-millimeter precision. Watch the mechanism in slow motion to appreciate the violence. Pneumatic top press rollers slam down with 500 psi of force, a crushing grip that immobilizes the curved trunk against the steel bed, flattening it into submission. In less than half a second, a 24-inch carbide-tipped circular saw drops from the gantry. The cut is effectively frictionless. The blade is spinning at such high RPM that the dried mud on the bark is atomized into a fine dust cloud before it can even smear the metal. The result is a billet, a perfectly sized 6-foot tube with clean, non-fractured ends. But the process is fraught with invisible danger. The lid technician monitoring the feed from the control booth isn't looking for speed. They are watching the shatter metric on their digital readout. If the moisture content of the incoming bamboo is too low, the ballistic impact of the blade will cause micro cracks to propagate down the length of the tube like a spider web on a windshield. These cracks are invisible to the naked eye now, but in 3 stages time, they would cause the entire slat to disintegrate under load. The intake process is a delicate balance of brute force and surgical restraint, turning a wild, unpredictable forest product into a standardized industrial unit ready for war. The standardized billets now move to the most violent stage of the initial breakdown, the JXY Star Blade radial splitter. This station is where the physics of the material fights back the hardest. Here lies the central problem of bamboo processing: hoop stress. Bamboo is a natural pressure vessel. It is a cylinder designed by millions of years of evolution to resist crushing forces. If you try to flatten it with a roller, it splinters chaotically, destroying the fiber bundles we are trying to save. To access the valuable fibers inside, we must overcome the cylinder's structural integrity without destroying the grain. We need to perform what engineers call industrial origami. The solution is the reverse bullet method. In a typical firearm, a projectile hits a target. Here, the target, the bamboo billet, is fired into the weapon. A massive 15-ton hydraulic ram engages the rear of the bamboo tube. Directly ahead sits a stationary tungsten steel star blade, sharpened to a razor's edge and arranged in a perfect 12-point radial pattern. It looks like the intake of a jet engine, but sharper. The machine doesn't cut, it bursts. Listen to the audio signature of this zone. It is not a whine, but a rhythmic deep that vibrates through the concrete floor. As the ram engages, the bamboo is forced over the star blade with unstoppable torque. Because bamboo is a unidirectional grass, it splits effortlessly along its length, if and only if the force is applied correctly. The blade acts as a wedge, converting the forward kinetic energy of the ram into outward radial pressure. In a fraction of a second, the darkness of the hollow tube is ripped open. The cylinder blooms like a flower, instantly transforming into 12 identical linear slats. It is a moment of violent geometric conversion. This transformation is critical. We have successfully converted a round 3D object into flat 2D planes that can be machined. However, the machine's tolerance is unforgiving. The self-centering iris feed wheels must align the bamboo perfectly with the dead center of the star blade.
Shut down
if the alignment drifts by even 3/16ths of an inch, the resulting slats will be asymmetrical, too thick on one side, too thin on the other. An asymmetrical slat will jam the high-speed molders in the next room, causing a catastrophic line stoppage that costs thousands of dollars a minute. The technicians here are obsessed with concentricity. They are ensuring that the biological pipe is dismantled with mathematical symmetry. The raw slats now enter the sterile processing zone. They are flat, but they are armored. The outer green skin of the bamboo, the epidermis, is essentially a biocomposite of cellulose and silica. Silica is the same mineral found in quartz and sand. It is waterproof, bacteria-proof, and, unfortunately for us, chemical-proof. If this skin remains, the downstream softening steam will never penetrate the wood, and the fiber will remain uselessly hard. We need a machine capable of stripping stone-hard armor without damaging the delicate meat underneath. The solution is the Weinig high-speed 4-sided molder. This is not a sander. It is a jet engine gem cutter. Inside the safety enclosure, 4 cutter heads are spinning at a deafening 12,000 RPM. The sound is a high-pitched, turbine-like scream that penetrates even heavy-duty ear protection. Standard steel blades would disintegrate in minutes against the bamboo's silica skin. Instead, these cutter heads are equipped with diamond polycrystalline knives, the only material on Earth hard enough to survive the silica onslaught. The operation here is supersonic surgery. The slats are fed through at a blistering 200 feet per minute. The top and bottom cutters engage simultaneously in a flurry of motion. The top cutter shaves off exactly 0.06 inches of the green bio-armor. Simultaneously, the bottom cutter planes away the interior node diaphragms, the internal walls of the bamboo that would otherwise disrupt the fiber flow. Visually, this is spectacular. Inside the machine, it looks like a blizzard of green confetti. The high-volume vacuum extraction system fights to inhale the blizzard of chips, while the slat undergoes a dramatic color change. It enters as a dark green rugged stick and exits, milliseconds later, as a pale cream-colored rectangle. This is the heartwood, but precision is the only thing that matters here. The tolerance is sub-millimeter. If the blade depth is too shallow, patches of green skin remain, which will create hard, scratchy defects in the final textile. If the cut is too deep, the machine shaves away the prime bast fiber bundles, literally turning profit into dust. To combat the natural unevenness of the plant, the machine utilizes floating head technology. Laser sensors detect the slight undulations in the bamboo's thickness and adjust the cutter head height in real time, riding the waves of the wood like an active suspension system on a sports car. It ensures that exactly the right amount of skin is removed, regardless of the slat's natural warping. We have stripped the armor. Now we must break the glue. The cream-colored slats are clean, shaved, and geometrically perfect, but they are still solid wood. If you try to bend one, it snaps with a sharp report. The fibers we want are locked together by a natural polymer called lignin, nature's superglue. It is the concrete matrix holding the rebar of the cellulose together. To liberate the fiber, we have to shatter the lignin without snapping the long cellulose strands. This requires the heavy-duty multi-stage roll crusher, a machine affectionately known by the engineering team as the Iron Jaw. This monolithic unit consists of 6 pairs of fluted steel rollers arranged in a descending series of gaps. The first pair has a wide gap, the last pair a hair-thin gap. The machine operates on the principle of controlled compression failure. As the rigid slat enters the first set of rollers, it is subjected to 1,200 psi of vertical pressure. Listen to the sound. It is not the clean hum of the slicer, but a dry, sickening rack crackle. It sounds like bone fracturing. That is the sound of the internal wood structure failing under immense load. The rollers are crushing the slat, creating millions of microscopic longitudinal fractures along the grain. Crucially, the rollers are fluted. They have deep vertical ridges. These ridges bite into the wood, forcing it to expand sideways. It chews the material, but never swallows it. It is a mechanical mastication process designed to fatigue the lignin bond until it surrenders. Watch the texture change at the output. The material that enters is a stiff board capable of being used as flooring. The material that exits is a ribbon, limp, fractured, and snake-like. It has lost its structural rigidity entirely. If you hold it up, it droops under its own weight. This is mechanically fibrillated bamboo. The lignin bonds are cracked, and the surface area has been increased by 1,000%. The wood is no longer a solid block. It is a bundle of loose strings held together by habit. It is primed and ready for the time machine. We leave the deafening noise of the mechanical floor and enter the humid, misty atmosphere of the hydrothermal retting zone. The air here is thick, smelling of wet earth and cooking corn, the distinctive olfactory signature of vegetable matter breaking down. In traditional fiber processing, retting involves leaving the plant in a swamp for 4 months to let natural bacteria eat the gums holding the fibers together. This facility does not have 4 months. It has 45 minutes. We are about to replace biology with thermodynamics. The hero of this phase is the continuous pressurized steam retort. It is a long stainless steel tunnel sealed by heavy industrial airlocks at both ends to maintain internal equilibrium. It resembles the hull of a submarine bolted to the factory floor. The crushed bamboo ribbons are fed onto a chain belt that carries them into the belly of the beast. Once the airlock cycles, they are blasted with saturated steam at 330 degrees PF and 58 psi of pressure. This is the time machine effect. By injecting high-pressure thermal energy, we are accelerating the laws of physics. We are simulating months of natural decay in under an hour. Inside the reactor, a process called hydrolysis occurs. The high heat dissolves the pectin and the remaining lignin glue that the mechanical crushers couldn't break. The steam penetrates the millions of microfractures created in the previous step, cooking the bamboo from the inside out. It is a chemical-free digestion process, using only water and heat to sever the molecular bonds. The visual shift is stark. Through the thick glass of the inspection porthole, you can see the ribbons darkening. They turn from a pale cream to a deep, rich, cooked brown. They are no longer wood. They are soft, pliable masses of wet cellulose. This stage is critically dangerous. If the temperature spikes past 338 degrees Celsius, the cellulose itself begins to degrade, turning the valuable fiber into carbonized mush and expensive charcoal. If the pressure drops, the pectin won't dissolve and the fiber will be coarse and wire-like. The control room monitors the thermal profile with the intensity of a nuclear plant operator. The goal is to melt the glue, not the product. The steamed ribbons emerge from the retort steaming, limp, and dark. They undergo a rapid drying phase to bring them to a precise moisture content of 12%. Now we reach the climax of the operation, the moment the wood officially becomes a textile. The material enters the Beamatic coarse opener and carding machine. At this stage, the useful fiber is still surrounded by parenchyma cells, short, blocky cells that make up the fleshy, non-structural part of the bamboo plant. In the textile world, this is called a dust. We need the long fibers and we need to banish the dust. The carding machine acts like a centrifugal ballet. Inside, a massive main cylinder covered in thousands of sharp angled steel pins is spinning at 4,900 surface feet per minute. Surrounding this main drum are smaller worker and stripper rollers, also covered in pins, rotating in opposite directions.
As the phalanx of machines
the metaphor here is simple but violent. Imagine brushing the tangled hair of a wild beast with 1,000 steel fingers moving at highway speeds. As the dried bamboo ribbons are fed in, the pins grab the individual fiber bundles and rip them apart from the parenchyma dust. Here is where physics takes the wheel. The useful fibers are long and light. They get caught in the teeth of the comb and float on the air currents generated by the drum. The dust and leftover node fragments are short and heavy. Centrifugal force flings them outward, where they fall through a grate into the waste collection system. This is the money shot of the factory. On the input side, you have dark, coarse, dried strips of wood. On the output side, an explosion of white, fluffy bamboo cotton erupts from the chute. It defies visual logic. Minutes ago, this was a rock-hard splinter capable of puncturing a tire. Now it is a cloud. The sound is a rhythmic, metallic swish. The sound of steel combing through millions of individual strands. The carding machine is the ultimate filter, separating the wheat from the chaff, or in this case, the textile from the timber. The resulting cloud of fiber is pneumatically conveyed through clear pipes to the final logistics zone. It looks like a pristine snowstorm rushing through a tube system high above the factory floor. Before it can be packaged, it must pass one final test. The stream passes through an optical scanning station. High-speed cameras inspect the flowing fiber for nebs, tiny knots of entangled fiber, or any remaining specks of green skin. A jet of compressed air shoots any contaminated tufts out of the stream with the accuracy of a sniper. This is zero-flow quality control, ensuring that only the purest cellulose makes it to the spinner. The pristine fiber descends into the automatic baler. A robotic plunger compresses the fluffy cloud with immense hydraulic force, compacting it into a dense rectangular block. The baler wraps the block in burlap and secures it with high-tension steel strapping. The final product, a 440-pound bale of prime-bast bamboo fiber. It is stamped, labeled, and stacked by a robotic arm with effortless precision. We started this process with a muddy, irregular, green steel pipe, a material so hard it breaks saw blades. Through laser mapping, hydraulic bursting, supersonic planing, compression crushing, thermal hydrolysis, and centrifugal carding, we have liberated the cellulose. And perhaps the most impressive feat is the sustainability factor. The camera pans to the boiler room. The green skin shavings, the no dust, and the rejected parenchyma cells aren't thrown into a landfill. They are fed into the facility's biomass furnace, the waste from the bamboo burns, to generate the very steam used in the retting phase. It is a closed-loop engineering marvel. The plant provides the energy for its own destruction. From the forest floor to the fashion floor, this is how high-tech bamboo is made.